Oh, okay. Are you ready, Robert?
Yes, I'm ready.
Okay, so welcome everyone. It's my big pleasure to introduce Robert Lazarsfeld from Stony Brook University. And Robert will speak about Cayley-Bacharach theorems and multiplier ideals.
Okay, well, thank you very much. Good, so I'm going to talk about Cayley-Bacharach theorems and a version involving multiplier ideals. And I'm going to start relatively, in the spirit of the seminar at Stony Brook and at Michigan, I'm going to make the first half or so expository aimed at people definitely non-experts and younger people. Okay, so I want to start by talking about the classical Cayley-Bacharach theorem, and I think I'll begin with an example / exercise. So here's the example / exercise. So let's consider two plane curves, so D1 and D2 and P2 of degrees D1 and D2. So I've drawn two curves here, meeting, and let's, for simplicity, assume they meet transversely at, in this case, D1 times D2 points. So Z here, this is this finite set of points at which these two curves meet. Good. Okay, so now let's choose one of these points, call it P. And what I want to do is I want to throw this point P away. So I want to remove P from Z, and I'm going to call what's left Z prime. So here, Z prime is just all these are brown. I don't know if you can see these brown points, but I'm throwing away the 1 point. And so the question is, what are the defining equations of Z prime? How do we find out the equations defining this set when we throw 1 point of intersection from two curves away? So how do we do that? Okay, so here's how that goes. It's kind of a fun story that you can give as an exercise to your undergraduate class. So, okay, so how should we do that? So let's say that D1 and D2 are defined by polynomials F1 and F2. So F1 has degree D1, F2 has degree D2. And this point P is the intersection of two linear forms. So let's call them L1 and L2. Okay, now F1 vanishes at P. So it means that we can write F1 as a linear combination of L1 and L2. So let's do that. So we write F1 as A11 L1 plus A12 L2. So A11 and A12 now are homogeneous polynomials of degree D1 minus 1. And similarly, we can write F2, the equation for the other curve, as a linear combination of L1 and L2. So here A21 and A22 are polynomials of degree D2 minus 1. So now we have this 2 by 2 matrix of the A's, and I want to let G be its determinant. Okay, so what sort of fellow is G? Well, G is a determinant of a matrix. The top row has polynomials of degree D1. The bottom row are polynomials of degree D2. So the determinant, D2 minus 1. So the determinant of G has degree D1 plus D2 minus 2. Okay, so here's my exercise. That if you take the complement of 1 point, if you let Z prime be this complete intersection Z minus a point, its ideal, its homogeneous ideal, is generated by F1 and F2 and this funny polynomial G. Okay, so that's my exercise. So one way, if you know about linkage, you can do it like that, but I assume there are various ways to do it, or you can give it as an exercise to your undergraduate class and see what comes in. Okay, so what's the moral of this? So this is supposed to, we're supposed to learn two things from this. So first of all, this is an example of the fact that you can take something that has quite simple equations, in this case Z, and throw away a point, and you can get new equations, more equations and new equations with higher degrees. And second of all, so what's a corollary of this little exercise is that it shows us that any curve of degree D1 plus D2 minus 3 that passes through Z prime, so all the points of Z other than P, must also contain P. And why is that? Well, we just decided that the ideal, homogeneous ideal of Z prime is generated by F1 and F2 and this polynomial of degree D1 plus D2 minus 2. So if we were to have a polynomial of D1 plus D2 minus 3 passing through the points of Z prime, it can't involve G, so it must be a linear combination of F1 and F2, and therefore it must pass through P. Okay, so this is one form of the famous Cayley-Bacharach theorem. So let me just state it like this. So the Cayley-Bacharach theorem says what we just learned. You take the transversal intersection of two curves in the plane of degrees d1 and d2. And let's call that finite set of points z. And then the theorem says that if you take any curve of degree d1 plus d2 minus 3, passing through all but one of the points of z, it passes through the remaining one as well. And just as a matter of vocabulary, I'll summarize this by saying that z satisfies the Cayley-Bacharach property with respect to curves of degree d1 plus d2 minus 3. So any curve of this degree passing through all but one of the points of z must pass through the remaining one. Okay, now when I talk about, when anybody talks about Cayley-Bacharach theorems, the term is used kind of generically. This theorem, as you probably know, has a long history. So one of the earlier forms is a version, I think, due to Charles, with the 8-9 point theorem for cubics. Any cubic through 8 of the 9 points of intersection of two cubics must pass through the 9th. It includes Pascal's theorem. And there's a paper of Eisenbud, Green, and Harris in the Bulletin in 1996 that goes in great length through the history of this theorem. I think Cayley's contribution was he stated a much more general form of the theorem, which had the drawback of being wrong. But Bachrach, in fact, proved corrected Cayley's statement. So there's a, let's see, okay. So there's this is maybe a little bit less known, but it's a nice statement that nicely generalizes this classical statement. So what does Bachrach's theorem say? So what you do is you write your original, your points at z. So again, z is still the complete intersection of these two curves. You divide it into two pieces, so two disjoint pieces. So you have z1 and z2. So you write it as a disjoint union of two non-empty pieces, non-empty subsets. And then you fix some number a that's less, I'm going to, for the moment, call s this magic number d1 plus d2 minus 3. And so what Bachrach's theorem does is it compares two gadgets. So on the left, we look at curves of degree s minus a. So this is s that pass through z2. So in other words, pass through all the points of z other than z1, but that don't pass through z. So this counts how many curves of degree s minus a pass through z2, but not z. And on the right-hand side, we get this H1 counts counts by how many conditions do the point Z1 fail to impose independent conditions on curves of degree A. So this is the superabundance of Z1 with respect to curves of degree A. And so what Bachrach's theorem says in this classical setting is that these two numbers are the same. And how do you recover the classical Cayley-Bacharach? Well, you take Z1 to be a single point, and you take A to be 0. So if Z1 is a single point, then an A is 0. Well, this is measuring how, if you take a single point, it imposes independent conditions on curves of degree 0, on constants. So the right-hand side is 0. And that means that the left-hand side is 0. So that's telling us that any curve of degree s that passes through all but z2, which is all the points of z other than p, must in fact also pass through p. So this is the Bachrach generalization of the classical Cayley-Bacharach theorem. Again, there are many proofs of this. I'll show you one. Well, I showed you one. I'll show you another one in a minute. My impression, again, I refer to the paper of Eisenbud now for the history. There's a nice, I think my impression is that these theorems were originally proved by studying linear series on plane curves. It comes down to the fact that if you have a curve in any Riemann surface and you take canonical plus a point, that point appears as a base point of that linear series. Okay, but again, there's nothing special about just curves in the plane. This statement generalizes very naturally to hypersurfaces in projective space. So what's the statement there? So you, again, in projective space, you start with n hypersurfaces of degrees d1 through dn, and you let z be their complete intersection. So again, for the moment, let's assume that z is the transversal intersection. So the number of points of z is the product of these degrees. And then the assertion is that it satisfies Cayley-Bacharach with respect to hypersurfaces of this degree. So the sum of the d's minus n minus 1. So in other words, any hypersurface of this degree passing through all but one of the points passes through the remaining one. So this is the version of Cayley-Bacharach for hypersurfaces in projective space. And again, the evident analog of Bachrach theorem also holds. Okay, now let me at this point make a remark that comes up that I'm not going to keep repeating, I hope, which is that for simplicity, I've stated the theorem by saying that we need the hypersurfaces to meet transversely. That's not really necessary. What you need is you need them to meet properly. And so Z is a zero-dimensional scheme of the Bezout degree. But then you need to worry about, in a complete intersection scheme like that, there's a natural notion of residuation. So if you have one subscheme, Z1, you can define in a natural array a residual one, Z2, and then all the statements hold. And it's quite, I mean, it's completely well understood how to do that. And that's not kind of our main concern. So I'm just gonna assume that these intersections are transversal, but keep in mind that that's completely irrelevant, but I just don't want to go there. Okay, so these are the Cayley-Bacharach statements for surfaces or hypersurfaces in projective space. And there's actually a huge commutative algebra literature on these things, much bigger. I think the commutative algebra literature is much bigger than the algebraic geometry literature. And it's always based, the sort of basic algebraic fact is that if you take the homogeneous coordinate ring of a complete intersection, it's a Gorenstein ring. And so there's some duality. And as we'll see, the whole theorem is very tied up with duality. So they're very interesting. For instance, Eisenbud and Green and Harris have some very interesting conjectures on how this theorem should generalize that are still very much open. So from an algebra point of view, it's still a kind of a pretty active area, but I want to turn now to geometry and try to look at this theorem as a statement in geometry rather than algebra. And as far as I know, it was only in the late 70s that people, in particular Griffiths and Harris, understood kind of what was the real geometric statement underlying these these Cayley-Bacharach theorems for hypersurfaces. And the idea is, their idea was you should really see it as a statement about the zero loci of sections of a vector bundle. So let me now explain that. So, okay, let's start with the smooth projective variety of dimension n. And let's look at a vector bundle on X whose rank is also n. So that's important. So the rank of the vector bundle is supposed to be the same as the dimension of the variety. And we're going to want to look at the determinant of E. So that's a line bundle, and we'll just call it L. So L is just what we use for the determinant of E. Okay, now let's imagine that we have a pretty nice section of E. So what's going to happen? Well, of course, if you have a section of a rank n vector bundle on an n-dimensional variety, you expect that to vanish at a finite set of points. So we're going to assume that this section vanishes on a finite set Z. And again, I want to think just for simplicity that this section vanishes simply transversely, so that let's say the graph of the section is transverse to the zero section. But again, that's just for simplicity. Okay, so we've got these, a section of a rank n vector bundle on an n-fold vanishes at a certain number of points. And of course, the number of points is computed by the top Chern class of it. So what's the statement of Griffiths and Harris? So what their nice statement is that this Z, this zeros of a section of a vector bundle, satisfies Cayley-Bacharach with respect to sections of the line bundle canonical plus determinant of E. So in other words, we take a section of the line bundle Kx plus the determinant of E, so that's a line bundle, and we assume that it vanishes at all but one of the points of Z, so all but one of the points of this zero locus of the section, and then the assertion is that it vanishes also at the remaining one. So this is the Griffiths-Harris version of the Cayley-Bacharach theorem. And of course, it immediately implies the statement for hypersurfaces, right? Because what do? You take X to be projective space, and you take E to be a direct sum of line bundles. And so if then a section of this E is given the complete intersection of hypersurfaces of degree d1 through dn, and then this kx plus L is hypersurfaces of this magic degree S. So the sum of the degrees minus n minus 1 for k. Okay, so this is kind of a much more clarifying statement, and I think I'm going to would like to show you the proof of it. Let's see idea of proof. So this is essentially, I think this is in their paper, and the idea of the proof is that it boils down to two facts: the exactness of a causal complex and then duality. Okay, so what is it that we want to prove? We want to prove that any section of kx plus L that vanishes at all but one of the points of this zero locus also vanishes at the remaining one. Okay, so we need to start by understanding this zero locus somehow. So the idea is that because the zero locus is zero dimensional, its structure sheaf is resolved by the Cazul complex. So I assume everybody knows what this is. You have a section O to E that gives you a map from E dual to O. You get a Cazul complex like this. And it's if you sort of remove the last term, what you get is an acyclic complex of length n that resolves OD. And the maps are just essentially given by contraction against S. Okay, and so the important thing is because Z is zero dimensional, in particular if it's transverse, this is exact. Okay, so now let's take this complex and twist through by the line bundle OX of K plus L. Okay, so what do we get? Well, we get OZ, K plus L restricted to Z. Here we get OX of K plus L. And I've written fewer terms, but on the left, what do we get? Well, remember that the determinant of E is L. So the determinant of E dual is L inverse, or L minus L. So when we twist by KX plus L, we're just going to get a KX. Okay, so here we have, again, omitting the last term for a minute, we have an acyclic complex of length n. It resolves this sheaf here, and the term on the left is just the canonical bundle. And that's a good sign. Okay, now just by chasing the long exact sequence of cohomology, what I claim is that we're going to automatically get this picture gives us a map, which I'll call delta, from the sections of the restrictions of Kx plus L to Hn of Kx. And this is a general fact. If you have a complex of length n that resolves something, you get a map from the H0 of the thing that's being resolved to the Hn of the term on the left. And what do? You just split this into short exact sequences. So we go from H naught here to H naught here to H1 of the kernel, H2 of that, and so on. And I'm sure everybody's done this. You chase this thing through, and eventually you get a map delta that looks like that. And it sits in a complex like this. So what I'm claiming, just again, it's the exact sequence. Any section of Kx plus L, a global section of Kx plus L, when you restrict it to Z, that has to be in the kernel of this funny map delta. So of course, what we're going to need the argument is going to be somehow if we had a section of Kx plus L that vanished at all but one of the points of Z, but not the remaining one, then we want to say it couldn't go to 0 under this map delta. So that means we better understand what this map delta is. And so here, this is where duality comes in. So as I say, Cayley-Bacharach is really very tied in with duality. So let's try to understand delta with shared duality. So let's start over here. So Hn of Kx is dual to H naught of Ox. So this is canonically dual to H naught of Ox. And well, I'm giving away the point, but it's okay. And what about this term here? Well, okay, we want to write that kind of canonically. So remember that Z is the zero locus of a section of E. So that means E restricted to Z is the normal bundle of Z. So L restricted to Z is the determinant of the normal bundle of Z. And so Kx plus L restricted to Z is the canonical sheaf of the dualizing sheaf of this finite set Z. So this, by duality, this H naught here is canonically dual to H naught of OZ dual. So what we have is a map that's, this delta is a map that's canonically dual to a map from H naught of Ox to H naught of OZ. And of course, there's not too much question about what it could be. So obviously, the only reasonable map from H naught of Ox to H naught of OZ is the restriction map. And so the lemma is that delta is dual under these dualities, isomorphisms from Serre duality to this restriction map. Now, of course, it couldn't be otherwise, but if you want to win a kind of a good citizenship award, at some point you do need to kind of sit down and decide, figure out how you really want to check something like this. I mean, it's not completely definitional. And so there are various ways to do it, but that's part of the game here. For example, you can think of OZ as being represented in the derived category by the Cazul complex, and then you can just write down duality for complexes and it pops out. But anyway, there is something to check here. Griffiths and Harris, I think, used residues. In the end, this is true. But now we're done, because what does this mean? This is just the restriction. So if you choose kind of obvious bases here, this delta is given by the map, by the matrix 1, 1, 1, 1, 1, 1, 1. It just sums up the sort of the values of these things at all these points. And so if you had a section of kx plus L that vanished at all but one of the points, if it didn't vanish at the remaining one, it couldn't map to 0 under delta. So you're done. Okay, so this is basically the Griffiths-Harris proof of Cayley-Bacharach. Again, it's 2 points. It's the exactness of the Cazul complex, and it's then duality. Okay, good. Now, what about Bachrach's statement? So this is actually less well known. So remember, Bachrach's statement in the classical cases, we wrote Z as a union of 2 disjoint sets, and then we looked at how one of them imposed conditions imposed on some line bundle, and then we looked at what happens to the other ones. And so there are results of Tan and Viveg, and they essentially study that question. Now, with no disrespect to Tan and Viveg, I think it's fair to say that they stayed pretty far away from a clean statement of what they were doing. So here's the result. It's essentially due to Tan and Viveg, but I'll give Lawrence and myself a little credit in small print for actually stating the thing. But here's what I hope is the right statement, the best. So again, the analog is this. We're going to again write Z as a disjoint union of 2 subsets, Z1 and Z2. And we fix an arbitrary line bundle A. And so we're going to introduce 2 numbers. So V1 measures the failure of Z1 to impose independent conditions on sections of A. And V2 is the number of sections of K plus L minus A that vanish on Z2, but not on Z1. And what the classical Cayley-Bacharach statement was those 2 numbers are the same. But here, you don't get that, but you get an inequality. This number of new equations is less than or equal to the failure to impose independent conditions. And again, the reason you don't expect equality is when you muck around with these Cazul complexes, we're not assuming any vanishings here. I'm not assuming any positivity. So when you muck around with these Cazul complexes on projective space, you get a lot of vanishings just because you're dealing with cohomology of line bundles that don't happen in general. But again, this is a statement that implies the classical one, again, in the same way as before. Take Z1 to be a point and take A to be the trivial line bundle. And again, then this V1 is 0-dimensional. A single point imposes independent conditions on constant functions. And so any section of K plus L vanishing at all but one of the points of Z vanishes at the remaining one. So this is, I think, a useful statement. People probably haven't looked at it as much. I mean, it should have applications beyond what's known. One thing you can do with it is to give clean proofs of Cayley-Bacharach type theorems due to sun for determinant loci, but I think I won't go into that now. Okay, so this is kind of my expository talk. Vanya, are there questions? Are there any questions?
So far, no questions, no.
Okay, so I'll go on to the excess vanishing. Okay, so what was the setting up to now? Well, again, we had a section of we have a rank n vector bundle on an n-dimensional variety. We take a section, so that should vanish at points. And then we wanted to say that that finite set of points satisfies Cayley-Bacharach with respect to a suitable line bundle. So in this case, Kx plus L. So now we want to start with the same setting as before. So we have an n-dimensional variety, a rank n vector bundle E. But now we'll take a section of E, but now we'll allow this section to vanish in more than points, in sort of higher dimensional loci than points. So let me, this condition we'll loosen this in a minute, but for the moment, imagine that the zero locus of S vanishes along two things. So a higher smooth variety W of some dimension little w, together with a nice set of points, a zero-dimensional set of points. So what's the picture you should have in mind? So imagine you have a curve in space, and you run three hypersurfaces of large degree through that curve. So what'll happen? So those three hypersurfaces will vanish nicely along the curve, plus it's some residual finite set. So the example here is and those three hypersurfaces, of course, are a section of a rank 3 vector bundle. So the picture you should have in mind are something like three surfaces in P3 vanishing along a curve plus some finite set of points. Okay. And the first person to kind of look at this was, there's this sort of general situation. It's a nice idea. It comes up in a theorem in a paper by Moulin Lee last year in the proceedings of the AMS. And so his idea was to try to give a Cayley-Bacharach statement in this setting. Now it's not completely obvious what you mean by a Cayley-Bacharach theorem. So his idea, which is I think the right one, at least it's what we're going to do in this talk. So who's supposed to satisfy the Cayley-Bacharach property? So really the way we've discussed it, it really only makes sense for points. So it's this residual finite, this finite collection of Z that's is going to be the fellow that satisfies the Cayley-Bacharach property. But it's going to satisfy it with respect to sections of some line bundle Kx plus L that somehow vanish on W in a suitable way. So the question we're going to ask is, if we take sections of Kx plus L vanishing on W, do those satisfy Cayley-Bacharach with respect to this finite dimensional set of points? Okay, so that's the theme. So let me now tell you what Moulin Lee's statement was, but it involves an additional hypothesis. So let me state that hypothesis. So imagine, just for simplicity, W is irreducible, or else this condition is supposed to hold component by component. So we have this smooth scheme W of some dimension little w, and it's cut out locally by n equations. And then what that means is that you're going to get an exact sequence from the actual normal bundle of W and Z that'll map to the restriction of E to W. So E to W is what would have been the normal bundle had the vanishing been proper. And then the quotient is some vector bundle V. So V is a vector bundle of dimension, I guess, dimension W. And if you know Fulton-McPherson intersection theory, for example, this is the bundle that comes up in their excess intersection theory. Okay, so here's Moulin Lee's statement. So we want to assume, he wants to assume that this exact sequence splits. So it splits as a sequence of vector bundles. And assuming that's true, what he shows is that this finite set Z satisfies Cayley-Bacharach with respect to the sections of Kx plus L that vanish on W. So in other words, if you take a section of Kx plus L that vanishes on W, and then if it happens to vanish at all but one of the points of Z, it also vanishes at the remaining one. Okay, so that's, I mean, it's nice. So the nice thing about this statement is that it, it tells you what's the right form for these Cayley-Bacharach statements in the presence of excess vanishing. So you look at sections of Kx plus L vanishing somehow on W, and you ask whether or not those satisfy Cayley-Bacharach whether or not the finite part of the intersection satisfies Cayley-Bacharach with respect to those. So that's the good news. The bad news is this hypothesis about the splitting of this exact sequence. So essentially it's never, in any real example, it doesn't split. So basically, as well, in practice, it basically never splits. So the question is whether or not, it's kind of a parasitic hypothesis, if you like. So the question is whether or not it's, let me backtrack for a sec. So he proves this theorem with some what he calls virtual residues. It's an analytic proof. I'm pretty convinced that you should be able to prove it by writing down the Kazul complex. And the splitting of this should somehow say that the maps that come into the Kazul complex somehow are trivial. So I'm quite sure there's a proof like that, but I have to confess, whenever I sit down to do it, I get all bollocksed up. But that should be, somebody should do that. But in any event, so as I say, the problem with this statement is that in practice, the hypothesis doesn't hold. In actual practice, it almost never splits. So the question then becomes, is the hypothesis really necessary for the truth of the statement, or is it just an artifact of the proof? And alas, it's easy to see that the statement, as stated, it fails. It can easily fail without if you don't assume the splitting of that sequence, that normal bundle sequence. So, and it's easy. I mean, you get counterexamples already on surfaces, but I think it's more fun to give an example in higher codimensions. So let me show you an example for curves in P3. So, okay, so let's consider the following situation. We'll take, I mean, it's basically the first thing you think of, you'll find that it fails. So take a rational normal cubic, a twisted cubic curve in P3, and our vector bundle E will be a direct sum of 3 line bundles. So I want to look at 3 surfaces passing through C. So I want to take general surfaces Q1 and Q2, those will be quadric surfaces passing through C, and F will be some surface of large degree D. Okay, so what's the situation I get there? Okay, well, I remind you that if you take 2 cubic surfaces through a rational normal curve, they intersect at the curve together with a line L, a secant line L, meeting the curve at 2 points. So Q1 intersect Q2 is this curve L plus this line, this curve C plus this line L meeting the curve at 2 points. And then when you intersect that whole thing with this surface, general surface F of degree D, what do you get? You get, so F meets the line at D points, but 2 of them are A1 and A2. So with this triple intersection of these 3 surfaces gives you C plus D minus 2 points on L. So the D points of intersection of F with L other than A1 and A2. Okay, so that's the 0 locus of this section of this rank 3 vector bundle. It's the curve plus D minus 2 points. And now the question is Lee's statement true? So what was Lee's statement? So we're supposed to look at surfaces of degree 2 plus D minus 4. So that's to say we're supposed to look at surfaces of degree D that vanish on C. And the question is, does Z satisfy Cayley-Bacharach with respect to surfaces of degree D passing through C? So in other words, if we take a surface of degree D passing through C, and if it vanishes at D minus 3 of these points down here, does it automatically vanish at the remaining one? And the answer is no, there's no reason it should. For example, you take a cubic through C, and you take planes through D minus 3 of these points, there's no reason those have to pass through the remaining one. And again, they're much easier counterexamples. I mean, you find counterexamples already for curves on surfaces. So unfortunately, this statement isn't true in general without the splitting of this exact sequence, which unfortunately almost never happens in practice.
Excuse me, and is there the example of possible of positive statement of splitting of this sequence?
You mean when does it split?
Yeah, at least one example.
Yeah, if you take a cone and stuff like that, sometimes it happens, but you have to, I mean, for example, if you do the same thing for curves, like if you take a curve on a surface, I mean, people have looked at that, but it's very rare. I think it's not that far from something being a complete intersection. It very rarely happens. You can find examples where it does. You take cones and stuff like that, but it basically, in practice, it rarely happens. But let me go back to this example here. So I want to say that we can, I want to sort of remember, so what we said is that the statement, if we look at a surface of degree D passing through C and all but one of the points of Z, they're not forced to pass through the remaining one. But let me sort of, I want to sort of make a funny remark here. Supposing we look at a surface of degree D that vanishes doubly along C and all but one of the points of Z. So then what happens? So imagine you have some surface of large degree that's double along C, so it has multiplicity along C, 2 along C, and it vanishes at all but one of the points of Z. Well, let's see how many times such a surface has to contain L. Well, the surface is double at C, so it meets L twice at each of these points A1 and A2, and then we're assuming it passes through D minus 3 of the other points of Z. So how many intersections have we accounted for on L? We've got D minus 3 plus 2 plus 2. So that's D plus 1. So in fact, our surface has to contain L. So what that means is if we take a surface of degree D that vanishes doubly along C, then the points of Z do satisfy Cayley-Bacharach with respect to that. So because they're forced to vanish along the whole line L. Okay, and that's an illustration of the first, I don't know if this is, that's an illustration of the first theorem I want to state. So this is all joint work with Lorenzine. Okay, so the theorem I'm gonna state says basically its exact generalization of what we looked at. So we have, suppose as above, we have a rank n vector bundle on an n-dimensional variety. And let's assume now that it vanishes along W union Z. So W is supposed to be some smooth set of dimension W, just as before. And Z is 0 dimensional. Again, let's, for simplicity, just assume it's transverse, so we don't need to worry about residuation. And now I want to assume that I have a section of Kx plus L that vanishes to order dimension of W plus 1 along W. So in our case of curves in P3, we wanted it to vanish twice along that curve. And then the claim is that, that if that section vanishes at all but one of the points of Z, it vanishes also at the remaining one. So in other words, we do get this set Z does satisfy Cayley-Bacharach in general under these hypotheses, but not with respect to all sections of K plus L vanishing along W, but we want to look at the smaller collection of sections of K plus L that vanish to order dimension of W plus 1 along W. Okay, so that's the first theorem. And again, there's an analogous statement a la Bachrach tan Vivek. You compare the dimension of again, there's no W with respect to the first set of points, and you divide Z into two sets. And the first set, you don't have any condition. And here you look at sections of Kx plus L minus A that vanish to high order along W, and you count how many vanish on Z2 and how many count on Z. Okay, so that's the first theorem. So again, I mean, what we saw whoops. It is, I mean, it's a strange statement, but at least it rescues this statement of Lee. But of course, there are two problems with it. First of all, I mean, why does it come in? I mean, it's non-conceptual. Why should you look at things vanishing to high order along W? And what if W isn't smooth? So again, I'm assuming that Z is smooth, but that's just for simplicity. But this statement, I really require W to be smooth. So what's this kind of doesn't seem like the right statement yet. So I want to kind of find the right statement that this is a special case of. And the idea is to bring in multiplier ideals. So, okay, so I'm going to give a 2-minute introduction to multiplier ideals. So, so imagine now you have some smooth variety of dimension X of dimension N, and it doesn't need to be smooth, compact or anything, but that doesn't matter. And we fix some ideal sheaf. Okay. And now what multipliers are is that there are some new ideal sheaves that are associated. I'm going to associate multiplier ideals to B and also its powers. I mean, B to the M is also an ideal, so that's fine. So I want to associate to B and its powers what are called multiplier ideals. And there's a long story about these, but intuitively you should think of them as measuring in a kind of a delicate manner the singularities of functions in B. That you take a general element of a general function element in B or in B to the M, that's a hypersurface, and you're measuring in some in some higher dimensional, typically higher dimensional way, the singularities of that. Okay, so let me give you two definitions. So the more intuitive definition that's not so easy for people like me and algebraic geometry to work with is an analytic definition. So again, working analytically, you choose local generators for this ideal. And then we're going to form this real valued function. So we're going to look at modulus. So I'm going to look, given a function f, I'm going to look at modulus of f squared divided by the sum of the squares of the moduli of the g's to the mth power. And I'm asking, the ideal is this consists of all functions that render that real valued function locally integrable at every point. So how do you think about that? So imagine you're sitting at a point where the g's don't vanish, away from the zeros of B. So you're sitting at some point where not all the g's vanish. Well, then the denominator is constant, at least is non-zero, and so 1 over it is locally integrable. So I can take, if I'm away from the zeros of the b, I can take the function 1 is in the multiplier ideal, so the multiplier ideal is locally trivial there. On the other hand, supposing I'm sitting at a point where all the g's vanish. Well, then what's happening is that the denominator is going to 0, presumably quite quickly. And so its reciprocal is going off to infinity. So to get an integrable function, I'm going to have to multiply on top by something that vanishes to presumably in some higher order way. And which functions I have to multiply by to keep it integrable is the multiplier ideal. Another construction that makes more sense algebra geometrically, but it's a little bit harder to, a little bit less intuitive, although if you played with singularities in the minimal model program, this of course will be quite natural. What you do is you take a log resolution of B. So you blow up until B becomes a principal. You principalize B and you ask that it, so you do some blowing up and you ask them when you pull up B, you should just get it, the function should vanish along a divisor B, which should have normal crossing support. And then this multiplier ideal of B to the M is just I take the relative canonical bundle minus M times B. So that's some collection of, and I push it down. So that's some ideal sheaf. And that's another way of defining the multiplier ideal. And you can kind of see, because this canonical bundle comes in, these are very, this expression here, this K minus MB, this is of the form canonical plus globally generated, plus ample for this map. And so you can see that these multiplier ideals are going to be very tied in with vanishing theorems. And they have a lot of wonderful properties coming from vanishing theorems, but I'm not going to really talk about that. Okay, so what's the one example that's easy to work out? So take a smooth variety W of dimension little w on X, and then as an exercise, you can compute the multiplier ideal of its ideal sheaf to the nth power. And what do you get? Well, if you have a smooth variety, a smooth subvariety, then its ideal sheaf is, you resolve its ideal sheaf just by blowing up. So the X prime is just going to be the blow up of this W. And then the exceptional divisor will appear in the relative canonical bundle with coefficient codimension -1, I guess. And so you just write this down and you see that what you get is the multiplier ideal sheaf here is just the ideal sheaf of W to the W plus 1 power. So that's, we've seen that before. And of course, that's where that's going to come in. Okay, so that's multiplier ideals. Let me now, so what should be the setup of, what should be the setup of Cayley-Bacharach with multiplier ideals? Okay, so again, we have some n-dimensional variety, a rank n vector bundle, and a section of E. And I want to assume, again, the zero locus of X should have a finite part and a random part. So I want to assume that X vanishes simply along a non-empty finite set. And again, the simply isn't important, but I just don't want to worry about residuation. And then it vanishes elsewhere in a completely arbitrary manner. So it vanishes arbitrarily along some subscheme defined by some ideal sheaf B. So the picture is a zero locus like this. You get a nice set of points Z and whatever you like away from Z. And to state this, to define this ideal B a little bit more carefully, remember that the map, a section gives us a map from O to E and hence from E to OX, E dual to OX. And the image of that map is an ideal sheaf. And we ask that the ideal sheaf be B times the ideal of this Z and that their support should be disjoint. So the ideal sheaf B is whatever ideal this section generates, the zero locus of this section away from Z. Okay, so what's the theorem? Then the theorem is that, now imagine that you have a section of Kx plus L, and what you ask is that it vanish along this multiplier ideal of B to the nth power. So n, remember, is the dimension. So I have a section of Kx plus L, and it's supposed to lie locally in this ideal sheaf, in this multiplier ideal of B to the n. And then the claim is that if H, if the section vanishes at all but one point of Z, then it vanishes also at the remaining one. So in other words, we're saying that the finite part of Z satisfies Cayley-Bacharach with respect to this sublinear series of Kx plus L. So the sublinear series, I look at all sections of kx plus L vanishing as they're required to vanish by this multiplier ideal b to the n. Okay, and so that's the theorem, the version of Cayley-Bacharach with multiplier ideals. So what are some examples? Well, if we go back to the situation we looked at earlier, this situation over here, so if the section vanishes along a smooth subvariety plus a z, then we're taking B to be the ideal of that smooth variety. And as we just saw, in that case, the multiplier ideal of B to the n is just I, the ideal sheaf of W to the W first power. So that's where theorem A comes from. Theorem A is the special case of this statement where we control in a nice way what the zero locus of the section is. Another example, this is how we got into this question, although I have to confess at the moment, this has to be a useful statement, but I haven't found out how to use it yet. But we were interested, I mean, there's been interest recently in understanding the geometry of load. I mean, what can you say if you have a variety and you write it as a generic, if you write it as a generic rational, as a generically finite rational covering of Pn, what can you say about the degree of that? And people have used the fact that the general fiber satisfies Cayley-Bacharach with respect to the canonical bundle. But there's the Cayley-Bacharach theorem for multiplier ideals gives a stronger statement than it satisfies Cayley-Bacharach with respect to this. And this is a bigger linear series than the canonical bundle. So in principle, this is a stronger statement, but I haven't yet figured out how to use it in practice. And then, of course, you can make up a lot of whimsical examples. So here's a question that I'm sure has occurred to a lot of you. Take a rational normal curve in degree 3 and P3, and take 3 general quintic surfaces passing doubly along that thing. So they vanish at C with some multiplicity, and if I've done it correctly, 125 other points. And so now you'll be happy to know that those 125 points satisfy Cayley-Bacharach with respect to surfaces of degree 11 vanishing to order 5. So you just kind of write these things down. And again, there's a spirit in the statement of Bachrach 10 Vivek. So again, we write Z as a disjoint union of two non-empty subsets. And V1 is always we choose a line bundle A. V1 measures by how many conditions Z1 fails to impose independent conditions on A. And the other dimension is we look at sections of Kx plus L vanishing along, minus A vanishing on the multiply ideal that vanish at Z2, but not on Z. And then we get the same inequality as before. Okay, so where does this theorem come from? So like many theorems about involving multiplier ideals, the proof is almost automatic. There's nothing to do. Somehow the whole idea of multiplier ideals is they always reduce to some statement with kind of non-excess vanishing. So let me quickly run through the proof, and you'll see that there's nothing, it really involves nothing other than the classical theorems. Okay, so where is this coming from? So remember, we have this section, this S defines a map from E to O, OX, and we're assuming that the image is B times IZ. So Z is the ideal of this nice set of points, and B is random. So what could you possibly do? You just take a log resolution of B, and you ask that it be an isomorphism over Z. So we'll say that the pullback of B is this is a divisor, so it's the sections vanishing along minus B, where B has normal crossing support. We'll write Z prime for the inverse image of Z in X prime, but remember, mu is an isomorphism over Z. So this Z prime maps isomorphically to Z. E prime will denote the pullback of E, and L prime will denote the pullback of L. Okay. Now, when we pull back this original section, so the section originally kind of cut out the ideal B, but when we pull it back, it's going to vanish. It's going to cut out this, this ideal sheaf O of minus B. So our original section vanishes along the divisor B. And so we can divide out by that divisor. And so we get a new section that vanishes. It's a section S prime of the line bundle E prime minus B. So in other words, we can twist out once you have a section that vanishes along a divisor, you can twist out the divisorial part of that. Okay, so now we get a section of E prime minus B, and this vanishes simply along Z prime and nowhere else because all the B stuff is absorbed into here. Now notice that we've got this E prime minus B is a new line bundle, and what's its determinant? Well, its determinant is L prime, that's the determinant of E, but now we get minus N times B because we got a rank N vector bundle, and we've twisted by a divisor, so the determinant goes down by the rank, changes by the N times that, the rank times that divisor. But anyway, now we've got a situation where we're exactly in the situation of Griffiths and Harris and Tan Dieweg, and so we're done. We just apply the theorem upstairs and we push it down. And you can kind of see when we push down, we're going to get a kx prime up. The theorem upstairs is going to involve some kx prime. When we push kx prime minus nb down, we're going to get kx times a multiplier ideal. So basically, there's nothing to do. It's just like many of these multiplier theorem proofs, it comes for free once you know the machinery. And I don't think you even need any vanishings here. Okay, so the theorem is itself free, but there's another way to look at it, which I find a more, so the theorem is free, but somehow it doesn't tell you kind of morally why it's true, perhaps. So there's another way of looking at why you expect Cayley-Bacharach theorems with multiplier ideals. There's another way to look at it that's, I mean, you could prove it this way. That's maybe a little bit less simple to prove, but I think gives you a kind of, to me, I like the point of view better. So let me tell you a kind of a more conceptual reason why you're really expecting to have Cayley-Bacharach theorems with multiplier ideals. Okay, so let's go back to the original Griffiths-Harris theorem. So we have some section S of a vector bundle. And what was the point of the Griffiths-Harris argument? The point of the Griffiths-Harris argument is that you form the Cazul complex, and that was exact. And the problem in general is that the failure of that thing to be exact is what's keeping the most naive statement from being true. But now, the idea is that so if you have a section that vanishes in a kind of a yucky, a section of a vector bundle that vanishes in a yucky way, the Cazul complex isn't exact, but there are some subcomplexes that are exact. And in particular, what multiplier ideals give you is that without any, well, the same assumptions on S as before, the Cazul, what the multiplier ideals give you, and here you need vanishing for multiplier ideals, they give you a subcomplex of the Skoda the subcomplex of the Cazul complex that is automatically exact. So I'm going to start in wedge n of E, but then when I multiply by S, S lies in the multiplier ideal of B. So I'm going to think of that as mapping into wedge n minus 1 of E dual tensor, the multiplier ideal of B. When I multiply by S again, I'm going to go into the multiplier ideal of B squared and so on. So I have these, I sort of take this thing and it's the same maps as before, but instead of thinking of it as mapping into the whole vector bundle, I'm thinking of it as mapping into subsheaves defined by these multiplier ideals. I just ran out of space here. So here I'd get J of B to the N, and then I'd get OZ, and I'm writing it as J of B to the N. So the theorem is that this always is exact. And this, again, you prove it by writing the Cazul complex upstairs and pushing it down. But once you know this is exact, then we could, if we wanted to, use the Griffiths and Harris theorem to deduce these Cayley-Bacharach for multiplier ideals from this. But the point I want to make is that what multiplier ideals conceptually give you is that they give you subcomplexes of a Cazul complex that are automatically exact. They somehow, the exactness is kind of built in for vanishing theorem reasons. And it's interesting, so I think of this as kind of a Kodaira type a subcomplex that's exact for Kodaira vanishing type reasons. But quite generally, there's also a subcomplex that's exact for Serre vanishing reasons. And this is a well-known fact in algebra. So if you take any Cazul complex like this, same hypotheses as before, you can use Serre vanishing to show that if you take a large integer p, again, you take wedge n of E times the pth power, you multiply by S, you end up in the p plus first power, and so on. So this complex is always exact for large p's. And so that's a kind of a Serre vanishing statement. But of course, you don't know exactly where that starts. So having a kind of a Kodaira vanishing statement is much more useful. Okay, so that's kind of it. I want to kind of close with two questions. So the first, which is kind of embarrassing, is so I spent an hour talking about this Cayley-Bacharach theorem for bundle with multiple ideals, but I have to confess that there aren't any really compelling applications yet. So first, a question is to find some applications. So two possibilities. One, I think, I'm hopeful eventually will lead to these things, is this thing I mentioned before. Use this Cayley-Bacharach theorem, this trace Cayley-Bacharach theorem to say something about degrees of rational coverings. Another thing one could look at, though again, I don't know any completely clear statements, is if I take a one form on an n-dimensional variety, it vanishes. Imagine it has some isolated zeros and some non-isolated zeros, and in principle, you get a Cayley-Bacharach type statement for the linear series 2K vanishing suitably along the non-isolated stuff. So the question is, does that have any interesting applications? But hopefully, eventually there'll be some applications. Finally, there's another question that occurs to me. I don't know whether this really makes sense, but the very first thing I talked about where we found the equations of that Z prime is what's really called liaison or linkage. So you have a small complete intersection, a big complete intersection, and it's a machine for telling you the equations of the complement stuff. So is there a theory of linkage or liaison which tells you about equations where you have excess intersections? So you have a complete intersection with some excess intersection, a small thing in there. Can you figure out what's going on in the remaining stuff? So again, I don't know whether this is whether there's a there, but it seems like it might be fun if it existed. Okay, so that's the talk, and I'm finished. So I'll happy to, if there are any questions.
Thank you, Rob, very much for a very nice talk. Let's thank Rob in Zoom and maybe like this. Okay, thank you very much. Before asking for questions, can I ask a question?
Yeah.
Basically, during your talk, I just was thinking about different possible applications, but in your theorem. But in my mind, it's very hard to control smoothness of W.
Right.
Like, can you remove this condition?
Well, so that's what I'm saying. So the way to remove it in general is you just let B. It's just this thing here. Yeah. So it's random thing here. So you need to, whatever you get some ideal, and then you want to compute its multiplier ideals.
Okay. Okay.
So what I was saying is that this statement here, this has no assumptions on B. But if you knew that B were the ideal of a smoothing, then you can compute its multiplier. So in some sense, there's no hypothesis like that necessary, but then it's governed by the multiplier ideal rather than any simple, just the ideal of
okay. Perfect. Okay, any questions? Please just to ask. Yeah.
Can I ask a question?
Yeah, hi Adrian. Yes, please.
Hello. So can you actually replace these multiplier ideals with test ideals in positive characteristic?
That's an interesting question. I'm not the right guy to ask, of course. I don't see, so well, we have to be a little bit careful. I don't know, because the problem is, let's see for a minute. The proof of the theorem was resolved singularity. So of course that's problematic. I don't think the proof of the theorem doesn't really use vanishing. On the other hand, I think the Skoda theorem these Skoda complexes aren't true with test ideals, because this Skoda complex implies these funny syzygetic properties of multiplier ideals, and I think those aren't true. So I don't know. I mean, I'm not the right guy to ask, but the proof where you just resolve singularities, I mean, you resolve singularities. So I don't know. But that's an interesting question. I don't know. I'd be a little bit nervous, because if you don't resolve singularities, you need something like this. And I don't think that's true with test ideals, but I could be wrong.
Thank you, Rob. Any other questions? Please ask. Okay, let me check the chat. No. Okay. I don't see any questions in the chat. Okay, Rob, it seems to me that there's no more questions. Thank you for very nice talk. I think it went very good. Thank you. And let's wait. There's some chat. Yeah. Okay. There's no questions in the chat. Okay. Thank you very much. Let's thank Rob in Zoom again, like this and like this. Thank you very much. Thanks.
Okay.
Okay.
So I'll stop my share.
Yeah, and I will upload the recording today a bit late in the evening.
Can I ask, how does one access, not for me, but for the other ones, how does one access these recordings?
It's on the web page of the Zach seminar. You just scroll down.
I see, okay.
And they are in chronological order in the bottom of the web page, all of them. There are tons of them. You just click, and we keep recording in the high quality separately, but then we upload just on the Vimeo web page, and but it's absolutely fine. I mean, all of them there, there.
Good. Okay. Well, thank you very much.
Thank you. And yeah, on Thursday we will have talk by Yuchen Liu from Yale, and also everyone is welcome. Yeah. See you. Thank you.
Bye-bye.
Bye.